So I'm going to try to make this a common sense approach to the pre-calc book of section 8.2 titled Relative Growth Rates. The main idea here in this section is really just trying to get you used to which functions are growing faster than others, and when one function grows faster than another, finding limits is when you know which functions grow faster, finding limits is actually pretty easy. Limits when x is approaching infinity, and that kind of brings us back to the Bubble Theorem. If you remember that, the Bubble Theorem, when we're taking limits as x approaches either positive or negative infinity of some function f of x over another function g of x, okay, so it's really for finding limits as x is getting really, really big, either in the positive or the negative direction. Okay, the Bubble Theorem, it just allows us to compare the relative growth rates. Now, we didn't say that before, but that's where we're at now. The relative growth rates of both the numerator and the denominator. It doesn't matter what the functions are. They could both be polynomials. They could both be exponential, logs, whatever. And that's what we're going to get more into in this section, the different kinds of functions besides just polynomials. Okay, but just to remind you that the Bubble Theorem states that when the denominator of a fraction is growing faster, and it doesn't have to grow that much faster, just a little bit faster in the beginning, when x gets really, really big, that makes the denominator a lot larger compared to the numerator, and therefore the limit is 0. Okay? And then likewise, when the numerator of the fraction grows either a little bit faster or substantially faster than the denominator, then we say that the limit is either positive or negative infinity. And then if the relative growth rates, meaning that the numerator and denominator are growing at the same rate, basically it's the same function with the exception of a coefficient difference in both the numerator and denominator, then we say that you just take the coefficient of the numerator and divide it by the coefficient of the denominator, and you've got your limit. So that's what we're going to focus on in this section. Okay, so keep that in mind. And just some basic functions when we compare the relative growth rates of an exponential e to the x, or a linear function y equals x, a log function ln of x, you can see hopefully clearly that the exponential functions grow faster than the polynomial functions, and the polynomial functions grow faster than the log functions. The log functions grow actually pretty slowly compared to the other ones. Okay? And so that brings us to limit problems like this. And so what I would encourage you to do when I show you a limit problem is just try to figure it out on your own first. And I'm just going to start with the limit as x approaches infinity of e to the x over x. Okay, well, we just finished with L'Hopital's rule, so you could see that this is infinity over infinity, or you could get to the limit quicker by realizing that, wow, wait a second, e to the x is going to grow a lot faster than x, and so we say that the limit is infinity, okay, because x is getting really, really big. Okay, I'm going to go ahead and put up a couple more limits and then pause the video and have you guys try a couple more before we get any further. Limit as x approaches infinity of x over e to the x, and then limit as x approaches infinity of e to the x over ln of x, and limit as x approaches infinity of, what do I want to do, x over ln of x. Okay, so try those, and I'm going to actually stop the video because my wife needs to talk to me.